Welcome students, welcome to the next session of structural analysis 2. So in the previous class we have started our concept moment distribution method. Then we have analyzed and statically indeterminate structure which is a proper cantilever beam which is subjected to some loading. Now we are going into continuous beam analysis using moment distribution method. As we have already said, the overall analysis involves the calculation of support moments, calculation of support reactions, generation of the actual bending moment diagram and generation of the shear force diagram. Okay, so the remaining three steps, generation of support reactions, bending moment diagram, shear force diagram, all will be same for any method we use. But the first thing is how we are calculating the support moments. Here I am using moment distribution method for calculating the actual support moments they are occurring. Okay. Firstly, we will go into the problem what they have given. So we should have to analyze the continuous beam shown in the figure. So without mentioning anything they have given the problem, that's why we should have to analyze for the support moments, support reactions, shear force diagram and bending moment diagram. All the things needed to be completed. Okay. So here I am having a continuous beam of a span AB as 4 meters and a span BC as 6 meters. And also this members are having subjected to a UDL over the lens. Okay, so in the figure they have given the first span is having a UDL of 6 kilonewton per meter and the second span is having a UDL of 10 kilonewton per meter. Why they have given these sizes difference? Just as when you see, you can observe something, these two are not same. By mistake also, you shouldn't want to keep the same load over the entire. That's why they have given in the picture itself. If they have not mentioned also, they are indicated the UDL values. Okay, the first length is having 6 kilonewton per meter and the second length or the second span BC is having 10 kilonewton per meter UDL over the length. Okay, for such a type of structure, in the beam itself, it is a continuous beam with the support A, B and C as hinged like conditions as we have seen. So I can say the support A and C are hinged or simply supported ends. Okay. The first thing for moment distribution method or for calculating the support moments in the moment distribution method, what is the first step we should have to do? We should have to calculate the distribution factors. Okay. So I am going into our step 1. So the step 1 involved is distribution factor calculation. Okay. Where the distribution factor will come? At a joint where it is having two span continuation. So this joint will have the distribution factor. How much amount this span should consist, how much amount this span should consist. So those joints only will have the distribution factors. Here I am having A, B and C. B is the only joint because it is having two members continuity. A is having 1, C is having 1, but B is having 2 members continuity. That's why the joint B will have distribution factors. We will calculate now. Okay. So, firstly, for that I am developing a distribution factor calculation table. So, the first thing, joint. If it is having 4 spans, so joint B and joint C will have. See, if it is A, B, C and D, maybe like this. Okay. So, in this condition, joint B and joint C, 2 members will have distribution factor. 2 joints will have distribution factors. But here, our problem is up to this. So, only the joint available is B. And the members connected to this joint are BA and BC. Yes. This is having A, this is B and this is C. If it is the structure. So this is our condition. Next, the next calculation is relative stiffness. So, relative stiffness formula. What is the relative stiffness formula? Relative stiffness is I by L. If end is fixed. Relative stiffness of a member is I by L, ratio of moment of inertia of the member by length of the member when the farther end is fixed. And the value of relative stiffness is 3/4 of I by L. Relative stiffness formula is 3/4 of I by L when the farther end is hinged. So, I am observing end B. So, the farther end is A or farther end will be C. So, if the farther end is fixed, then I will calculate I by L, moment of inertia of the member by length of the member. If the farther end is hinged, I will calculate the relative stiffness as 3/4 I by L. Here, the two members are farther ends having hinges only, simply supports, right? So, the simply supported ends are there. That's why the relative stiffness is equal to 3/4 I by, what is the length of the span AB? That is 4 meters. And here also 3/4 of I by 6, right? So, 4 meters and 6 meters. They have not mentioned in the problem. This is having different moment of inertia. If they mention only, I can take they are different. If without mentioning, I can take simply it is I. Why I kept I? Because later in the ratio of distribution factor that I will be cancelled. So, no need to think more. Simply I is moment of inertia of AB and BC because they have not mentioned anything. So, I is simply My, that is the moment of inertia for AB and BC spans. And then the total relative stiffness calculation. The next thing is total relative stiffness. The total relative stiffness calculation. Simply summing up these two is 3/4 I by 4 plus 3/4 I by 6. So, summation of these two is total relative stiffness at the joint. Now, the distribution factor is DF. The distribution factor is equal to relative stiffness of the member divided by the total relative stiffness. So, I by 4 by I by 4 plus I by 6. And for the bottom one, I by 6 by I by 4 plus I by 6. As I am cancelling 3, you want to, you can cancel I also. I am simply removing I and keeping 1 as is. Three by 4 of I have removed and I kept 1/4 by 1/4 plus 1/6 and then 1/6 by 1/4 plus 1/6. So, base as it is. Top is the corresponding relative stiffness. Taking the ratios out, we will calculate the distribution factors. And please try to keep the distribution factors in factors only. Don't keep it in the decimals because when you give so much of correction in the starting itself, the overall steps will be continuously do like that. So, in your calculus, you will have that part. So, when you sum up and give the answer, keep in the ratios only, not give it in the decimals. Okay, that is useful for you only, right? So, this is the answer for the distribution factor, and after calculating that, the overall table may appear like this. So, step 1, the corresponding distribution factor calculation. Firstly, joint B and then members BA and BC. And the corresponding BA members relative stiffness 3/4 of I by L and then 3/4 of I by L, and the total relative stiffness summation of these two, and then the distribution factor is individual by total, individual by total. So, we have got 3/5 plus 2/5. So, the distribution factor for the member AB or BA is B towards A. That's why you are writing BA. Okay, distribution factors for BA is 3/5. Distribution factor for this is 2/5. Okay. Now, after calculating the distribution factors, we will keep it aside and we will think about the fixed end moments. Okay. So, before entering into the distribution table, we should have to calculate the fixed end moments. So, the fixed end moments, how we will calculate? The step 2, fixed end moments. So, considering each span as span A with B beam and load and length. Similarly, span BC, considering each beam as a fixed beam subjected to the given load what they have applied, the corresponding fixed end moments as a fixed beam with UDL over entire length. The corresponding fixed moment formula is WL square by 12. So here I am using the same WL square by 12. So the first thing, W and L will differ. For the BC span, W and L will differ. Okay. For the first span, how much we have observed? 6 kilonewton per meter and 4 meter. 10 and 6. Okay. As it is in the anti-clockwise, that is minus. Please remember the sign conventions. Only the process will not give anything with the sign conventions only you should have to develop. So, minus 6 into 4 square by 12 we have got minus 8 kilonewton meter as the fixed end moment at A in the anti-clockwise direction, and on the right side of A, that is BAs. So, MAB, MBA, MFAB in the anti-clockwise direction, that's why I have indicated as minus 8, and MFBA, that is plus 8 because it is clockwise. For our moment distribution method, anti-clocks are negative, clocks are positive, same like the slope deflection. Okay. So, anti-clocks are negative, clocks are positive. Similarly, for the BC, anti-clocks are negative, clocks are positive. In this way, we have calculated the fixed end moments. Now, the main step is coming, that is generating the moment distribution table. Developing the moment distribution table. So, distribution of moments that is generated in the table. How we will start that? Firstly, we should have to write the joint members with some distance. Yes, I have indicated the joint members. And then, at which locations I am having the distribution factor? At joint B, I am having the distribution factor. Okay, so next, at B, indicate this. On the left, regarding BA, what is the distribution factor? That we should have to write here. How much we have got as the distribution factor? That is 3 by 5. And the next one is 2 by 5. So, this is 3 by 5 and this one is 2 by 5. So, 3 by 5 is distribution factor at B towards A. Distribution factor at B towards C is 2 by 5. And once you calculate, maybe if by mistake, maybe in decimal you have taken. Once do the check, summation of these two at a joint, summation of distribution factors should be equal to 1. Maybe if some value you have got as 0.25 and the next thing you have corrected as 0.74. Don't keep that. Summation should become 1. So the correction should be like maybe it is for 7.5 or it is for 2.6. The summation should give 1. In this way, you should have to keep the distribution factors. Here, that is a cross check. Whether you have taken the distribution factor table properly, this is the cross check. Summation of distribution factors at a joint should be equal to 1. Okay. So, I am writing those distribution factors in the distribution factor table. So, joint names, distribution factors indication, and then we should have to indicate the fixed end moments. So, in this way, A, B and C, and these are the fixed end moments we have developed, the distribution factors we have indicated. And at A, what is the fixed moment? At B towards A, what is the fixed moment? At B towards C, what is the fixed moment? At C towards B, what is the fixed end moment? Those answers I should have to write at the corresponding places. So, this is the places meant for those answers. Okay. So, at A towards B, minus 8, at B towards A, plus 8, and then minus 30 plus 30. Minus 8, plus 8, minus 30, plus 30. So, this is the first developing the step of moment distribution table. So, for the moment distribution table, we will write A, B, C like this, and then at which joint I am having the distribution factors with a vertical line on the left and right. I am indicating those distribution factors, and then we will draw a line so that From that you can generate the distribution factor table properly. Then we will indicate the fixed end moments at each corner towards the other span. Each corner towards the other span. Each corner towards the other span and the corner towards this span. So in this span I am generating A, AB, BA, BC, CD. Okay. These are the fixed moments we have generated. And when you see the picture, you may appear like this. So A, B and C. No need of indicating this is support line. Just simply A, B, C also you can indicate, or you can develop like a table. Okay. So you can indicate it like a table. So those distribution factors and fixed end moments we have given as it is. And the next step is distributing, how the moment is distributing for the supports. And you see here, at A I am having -8, at B I am having two different answers, at C I am having one answer. But in the actual structure, A support and C support are simply supported ends. So after writing this line, you should have to observe the original structure. After writing these fixed end moments, we should have to observe the original structure. There you observed that supports A and C are simply supported ends. So the support A and support C will have simply supported end. The corresponding moments should be equal to 0. Simply supported ends should have 0 moment. Okay. So that's why the correction moment will come. Like yesterday we have done for the propped cantilever. At the prop there is 0 moment. That's why the corresponding correction, and from the correction some balancing has come, right? So here also correction moment at A and correction moment at C needed to be applied. So simply supported ends, correction moments needed to be applied. So due to the simply supported ends, the correction moments needed to be applied, and also due to those correction moments, the corresponding carryover moments will be carried to the other end of the span. Okay. So as I am adding correction moment at A point. Okay. At A I am giving some correction moment, and the carryover moment will be given to the other end of the span. Okay. So as we have got this B, A and C, with ratios 3/5 and 2/5. These are the distribution factors, I think. 8, 8, 30, 30. So now the support A is simply supported end. Yes, the support A is a simply supported end. So that what comes for making the correction, I should have to add +8. Only directly I am adding it. Similarly, at C I am observing +30. So I should have to add -30. Okay, addition happened. Now the carryover moment will come. So as the addition has happened, the corresponding carryover moment should be transferred to that point, and as it is with the sign but in the half a quantity. So that is +4. Again there it is -30, that's why it is -15. So simply supported correction moments we have developed, and then the corresponding carryover moments are carried like this. Okay. So this is the next step of developing. Firstly, joint indication, distribution factor indication, and then fixed end moment indication, and then observing the original structure, giving the correction moments, and then from the correction moments any carryover is there, that carryover is transferred to the corresponding spans. Okay. So this is the way we have generated, given fixed end moments, distribution factors, and the corresponding correction with the as it is sign, but half the quantity I will give here with as it is sign. Whatever the sign I am using here, with the as it is sign, but half the quantity I should have to keep here. As it is sign, half the quantity. Okay. This is the next step. Now, after giving these things, we should have to give the finalization by indicating two solid lines which are very closely spaced. Okay. So the final moments needed to be written after two closely spaced lines. Why it is particular? Because in this method, how we will develop, in the way only our brain will recognize or recall. Okay. So only we have observed fixed end moments, and then we have observed the original structure for the end corrections. Okay, correction moments. So those correction moments and the corresponding carry was only completed. Now the main thing started by drawing two solid lines which are very closely spaced, and then what we should have to do? After these two lines, we should have to sum up whatever on the top it is there. So on the top, minus 8 and plus 8 were there, so minus 0. And this is summation, and its summation, and its summation. So okay, so the final moments needed to be added and written after the two closely spaced lines. In this way we have generated. The next thing, the main distribution. Till now we have outer only fixed end moments, only due to support conditions. Now I am coming into the main distribution process using the distribution factor. Okay, what is that? So the main distribution process will start now as follows. So how it is starting? Once you see here, this is 12 and this is minus 45. So at this joint, okay, at this joint only the process will start. Now I should have to sum up these two. 12 as it is with minus 45. Summation has given me 12 minus 45. I have got minus 33. Okay, so the final balance or the moment at this is minus 33. Okay, so at this joint I have observed minus 33 as unbalanced force. This at a joint, those two moments on the left and moment on the right should be equal, right? But these two are unequal. How much they are unequal? With an unbalanced amount of, as it is a summation, 12 as it is and minus 45. That quantity I have got minus 33. So for balancing that, I should have to add plus 33. Okay, I have to add plus 33 here. So 12 minus 45, I have got minus 33. Then for balancing that, plus 33 will be added there. Okay, only 33 is there. That plus 33 will be added at B. And how much I should have to add for BA? How much I should have to add for BC? That is according to the distribution factor. Okay, in that 33, it will be distributed to two spans. Okay, two spans it will take. And according to the distribution factor of the span, and the corresponding moment will be added as shown below. Okay, so we have got the corresponding final moments with 0, 12, minus 45 and 0, and here we have observed it is 3 by 5, it is 2 by 5. Okay. Now the net unbalanced force I have got is minus 33, and for balancing I have given 33, and in this 33, in this plus 33, some quantity will be given here, some quantity will be given here. How I will give individually? Based on the distribution factor of the span. Now plus 33 into 3 by 5, whatever the summation. This 33 you can't see in the table. These two summation you can't observe in the table. Whatever the things I should have to write, that only I will develop here. Okay, 12 and minus 45. Summation you should have to write in the rough. Okay, that rough answer should be multiplied with minus, because these summations has given some unbalanced force. With opposite sign only I can balance. So that unbalanced force I have got, and the balanced means the same quantity in the reverse sign convention I should have to add. In that quantity also, some will come this way, some will come this way. So that value of unbalancing converted into balancing, and that should be multiplied with the corresponding distribution factor. So plus 33 into corresponding distribution factor for this span 3 by 5, and I have got plus 19.8. So this plus 19.8 will be written at the joint for the span B towards A. Okay, so for the span B towards A. See here, plus 19.8. Why it has came? This 19.8 came because these two summation has given me minus 33. That minus 33 is the unbalanced force at the joint, because these two should be equal. Okay, in the opposite sign. Okay, summation those two should be equal to 0 with the joint equilibrium, right? So the joint equilibrium summation of these two should be equal to 0. But here the summation is still minus 33. For unbalancing that, plus 33 is added, and that 33 is distributed some part here and some part here. In the plus 33, 3/5 of plus 33. So how the distribution factor is there? That quantity into 33 has given here, and that value we should have to write here. And the same plus 33 value only in that 33, 2/5 of the portion is coming here. That answer I have written here. So 33 into 2 by 5, that is equal to 13.2, and will be written at the joint B towards C. So BC span. Okay. These wordings, no need to explain. Only thing you observe is starting calculation of distribution factor, calculation of fixed moments, and directly you will observe this table only. This table itself will explain all the things. What you have written one by one, what you have written one by one, all the things will be explained from the table only. Okay. Now, you see here, the next part, again, the vertical addition of the moments. So, the vertical addition of the moments will be carried if the support is fixed. Some part will be carried here, but it is 0 only. So, there is no carryover moment to the support. So, as it is, this value is there. So, this summations we will do. If it is fixed, again, how much I have added, the corresponding carryover will be transferred here. How much I have added here, the corresponding carryover will be transferred there. Okay. So, these are the answers, and this summation of these two. Okay. After summing up, you have observed 0, the same 0 I am keeping. And here, once you have drawn this line, please don't see the top. After adding only, I have got this. Again, don't see the top. This solid line indication is for that only. Once you have given the value, no need to observe the top for again summing up from the top to the bottom. Only you have added these two, and I have got this answer. Whatever the next values you have got, from that only I should have to add and indicate. So, 12 and 19.8. Addition of these two, we have got that as 31.8. So, that is the final support moment at B towards A. And then on the right side, minus 45 and plus 13.2. And we have got minus 31.8. So, this is the support moment at B towards C. And at C is 0 as it is. So, finally, we have got the distribution table like this with the vertical addition. And please remember, these solid lines above portion you will not consider. Once you have given this, that is final only. So, after observing, just now only we have mentioned the value at the joint on the left and the right. The summation of those two should be equal to 0. This joint equilibrium we have observed so many times. So, MBA plus MBC should be equal to 0. After observing that, you can stop the calculations. Otherwise, again, how much unbalanced is still there? Again, we will add these two. If it is 0, okay. Or if it is having some more quantity, again, from that quantity into the distribution factor, again, we will continue the process. So, these two's summation, if it is equal to 0, we will stop there. If these two's summation is not equal to 0, the corresponding unbalanced force is converted to balancing, and that balancing force is multiplied with the distribution factor. Okay, balancing force into the distribution factor, that answer again will be added here. In this way, the cycle will be continued for making these two values either equal or the summation is near to 0. Maybe some decimals 0.0 like that may come because of our corrections, but generally it may be equal to 0. The summation, these two may be equal to 0, so that we will stop the calculation. Okay. After observing at the joint, the sum of moments for the BA and BC, that is equal to 0. The distribution method can be stopped. Okay, we can stop. So, like we have already observed for the joint equilibrium, which is MBA plus MBC is equal to 0. In this way, I will conclude the table with a line. So, the indication of distribution factors, joints, fixed end moments, the correction moments for the simply supported ends, and then the unbalancing force, the unbalancing forces carryover moments, and all we will complete like this. Okay. Now, when you indicate the part, you can observe the supporting moments. Okay. Supporting moment at A, that is equal to 0. Supporting moment at B, that answer. See here. when you observe each individual figure, individual spans we have considered like this. This is hogging, this is hogging. And here, if it is clockwise, it will be considered positive in case of the moment distribution method. In the first span, clockwise, then it will be positive. So, in the first span, right end, having positive means at that end that is clockwise. But generally, at the support, when it is like this, it will cause hogging moment only. With as it is quantity, the answer is hogging. With the as it is quantity, the answer is hogging. So, 31.8 hogging. Or then it is like this anti-clockwise. So, anti-clocks moment distribution method will indicate as negative answers. Anti-clockwise as moment distribution method will indicate as negative answers. Okay. So, here whatever the answer has appeared, that needed to be multiplied with a minus, and that should be indicated as hogging, the same quantity of hogging. So, minus 31.8 indicated at the left support and acting in this direction will be negative. For what? For moment distribution method only. For us, that is an hogging moment with the quantity. Hogging moment with this quantity. So, the finally support moment at P is 31.8 hogging. Again, support moment at C is 0. Whatever the thing you have observed, 0, 0, and here only observation is as at the right side clockwise positive. That's why in the hogging condition B is positive, or at B towards C anti-clockwise they have indicated, and the corresponding anti-clockwise is negative indication. So, the overall indications are giving only the thing at B there is a hogging moment of 31.8 kilonewton meter. So, 31.8 hogging moment. Now, when you go further, this is the first step or completion. Okay. So, for generating this answer only we have chosen this moment distribution method. Now, you can go into the bending moment diagram generation. How I can go into the bending moment diagram generation? That actual bending moment diagram will come from merging the free bending moment diagram with the support moment diagram. Okay. So, now I am going for the free bending moment diagram. So, then I have to draw the free bending moment diagram. The actual bending moment diagram, the step involved is free BMD. Okay. That free BMD, how I can calculate? Taking each span as a simply supported beam with UDL. So, 6, 4, WL square by 8. So, 6 into 4 square by 8, some parabolic portion. Okay. So, 6 into 4 by 8 with 6, 4 square by 8. And the next thing is again a parabolic portion, 10, 6 square by 8. So, in this way, we will complete the free bending moment diagram. Once the beam is simple length, you may have combined loads. But if it is having continuous spans, they will directly give point load at center, UDL or eccentric point load. Okay. In some cases, in the next you may have couples also, that also will generate. Okay. So, point loads, UDLs and eccentric point loads. So, those free bending moment diagrams you can directly write from the known formula WL by 4, WL square by 8, WAB by L. In this way, we will write the free bending moment diagrams maximum moments. Okay. So, in this way, we will calculate the corresponding answer and indicate it as free BMD for the structure. So, this is the free BMD for the structure. Now, the actual bending moment comes in the the superimposing we are doing now. Now, that actual superimposing will continue from 0 to, initially free bending moment diagram generation, and then 0, a hogging moment. For the support moments, hogging will indicate above the line only from 0, B point and C point. And at B I have observed 31.8. So, connecting with a simple straight line, this ABC support moment diagram has we have got. and then we will indicate the, based on the shape, you can get that corresponding actual bending moment diagram. Again, one more thing you should have to remember is how we will indicate the baseline as the reference. Here, I will indicate the support moment line as the reference. So, above the support moment, whatever is the area that is positive. Above the support moment, whatever is the area that is positive. Below the support moment line, whatever is the area that is negative. Okay, so positive indication and negative indication, and they have given some values. See here, this is the value we know, and there is 29.1. Okay, once you know the individual free BMD heights, only for this structure what is the height I know, and also for a triangle with 31.8 over length and of 6 meter and at a distance of 3 meters, whatever is the height I can develop, right? So once it is from 0 to 6 meters, that is 31.8. From 0 to 3 meters, what is the height in the triangle? So from the triangle and from the parabola height, because this is happening at 3 meters only, the maximum will come at center. That's why at 3 meters, the parabola is having this height. At 3 meters, the triangle is having this height. Using those two answers, and final height, remaining leftover height is 29.1 at the center of this corresponding BC span. Similarly here also, again you will observe a triangle and you will observe the height at the center. Using those two answers, you can evaluate this answer. If you are enough okay with individual things, they may not observe the moments. Okay, don't think much for calculating this, because the problem itself will take some time for completion. Okay, initially what are the steps you should have to do? That you should have to remember. Starting distribution factor calculation, and then fixed moment calculation, and then indicating distribution factors and fixed end moments, and then observing the original structure, and applying the correction moments at the supports. And then due to the correction moments, there is some carryover moment at the spans. And after that, the correction moments and carryovers are over, we will get the final moments. So indicating at the simply supported ends 0, and at the B joint some answers were there. Now the main balancing or the main distribution we will start. So in that main distribution or balancing step, the corresponding answers we will get with distribution factors, the net unbalanced force, and the remaining things. So the net unbalanced force, the corresponding balancing thing, and then distributing it to the two joints. So distributing it to the two joints, in this way we will complete. And finally, below the lines, below the things, whatever thing you have observed, and adding these two answers, you will get the next step. Addition has given me some more answer. Those two answers, if they are nearly equal and its summation is becoming equal to 0, you can stop the problem there. And summing up, we have given the corresponding support moment answers, and the support moments are given like this. And then the free bending moment diagram we have generated. Merging the free bending moment diagram and the support moment diagram, you will evaluate the actual bending moment diagram. In the next class, for the same problem, we will generate the actual support reactions and actual shear force diagram, and then we will go into some numerical. Thank you.